Hello, friends. I'm glad to see you on the channel. Today we're diving into one of the deepest and most fascinating topics in modern science. What does quantum theory say about the nature of reality? This isn't just a conversation about particles and equations. It's an attempt to understand what the world is truly made of and why, at the most fundamental level, it behaves so strangely. Classical physics, based on the work of Isaac Newton, described the universe as a vast, precise machine. According to that worldview, if you knew the position and velocity of every particle, you could predict the future with absolute certainty. Reality seemed stable, objective, and completely determined. But the 20th century changed everything. It began with Max Planck, who discovered that energy is not emitted continuously, but in discrete packets, quanta. Soon after, Albert Einstein showed that light itself behaves like particles called photons. These discoveries marked the beginning of a scientific revolution. In the 1920s, physicists such as Werner Heisenberg, Erwin Schrödinger, and Niels Bohr developed the mathematical framework of quantum mechanics. And this is where reality started to look very different from everyday intuition. One of the most famous results is the uncertainty principle. It states that you cannot simultaneously know both the exact position and exact momentum of a particle. This is not due to imperfect measurement tools. It is a fundamental property of nature. The more precisely you determine a particle's position, the less precisely you can know its momentum, and vice versa. At the microscopic level, reality does not possess sharply defined properties in the classical sense. Another astonishing feature is superposition. A quantum system can exist in multiple states at the same time. An electron does not orbit the nucleus like a tiny planet around the sun. Instead, its state is described by a wave function that gives probabilities of finding it in different locations. Before measurement, you cannot say where the electron really is, only the probability of detecting it somewhere. This leads to the famous measurement problem. What exactly happens when we observe a quantum system? Why does it appear to choose a specific outcome? In the Copenhagen interpretation, the wave function represents a range of possible outcomes, and measurement leads to a collapse into one definite state. However, what precisely counts as a measurement remains a subject of debate. Importantly, in physics, measurement refers to physical interaction with a measuring device, not the mystical power of human consciousness. While philosophical discussions sometimes explore the role of the observer, quantum theory itself does not claim that thoughts create reality. It describes physical interactions between systems. One of the most remarkable phenomena discovered is quantum entanglement. Two particles can become correlated in such a way that measuring one instantly determines the state of the other, even if they are separated by vast distances. This effect has been experimentally confirmed and forms the foundation of quantum cryptography and quantum computing. Einstein famously referred to entanglement as spooky action at a distance. He hoped that hidden variables would restore a deterministic picture of reality. However, experimental tests of Bell's inequalities demonstrated that local hidden variable theories cannot explain the observed correlations. At a fundamental level, nature exhibits non-local features, though without allowing faster-than-light communication. So what does all this tell us about reality? There are multiple interpretations. The many worlds interpretation, proposed by Hugh Everett III, suggests that the wave function never collapses. Instead, every possible outcome occurs each in its own branch of the universe. This is not science fiction but a mathematically consistent interpretation, although there is currently no direct experimental evidence for the existence of these parallel branches. Another approach, known as Bohmian mechanics, introduces hidden variables and a pilot wave guiding particles. It restores determinism but accepts non-locality as fundamental. There are also relational interpretations, where properties exist only relative to other systems. In this view, reality is not made of independent objects with intrinsic attributes, but of networks of relationships. Some physicists even explore the idea that information might be more fundamental than matter. In certain theoretical frameworks, space and time themselves may emerge from deeper quantum processes. These ideas are still under active investigation, but they push the boundaries of how we understand existence. Quantum theory also shows that the vacuum is not empty. Even in empty space, quantum fluctuations occur. Particle-antiparticle pairs can briefly appear and disappear within the limits allowed by the uncertainty principle. At the deepest level, reality is dynamic and restless. When we ask about the nature of reality, it's important to remember that quantum mechanics is one of the most experimentally successful theories in history. It underlies semiconductors, lasers, MRI machines, and modern computing technology. This is not abstract speculation, it is a framework that works with extraordinary precision. And yet, the philosophical mystery remains. We can calculate probabilities with astonishing accuracy, but we cannot definitively say what really happens between measurements. Reality appears less like a collection of solid objects and more like a structure of probabilistic laws. Some researchers suggest that the universe may be fundamentally composed of processes rather than things. Particles are excitations of fields. Fields are quantum entities. And perhaps beneath them lies an even deeper layer that will one day unify quantum mechanics with gravity. The search for quantum gravity continues. Some approaches propose that spacetime itself has a discrete structure. Others suggest fundamental strings or additional dimensions. So far, none of these theories has received decisive experimental confirmation. But they expand our sense of what reality might ultimately be. One of the most profound lessons of quantum theory is that properties are not always independent of context. In classical physics, objects possess definite characteristics whether or not we observe them. In quantum physics, measurable properties arise in specific experimental setups. This does not mean reality is an illusion. It means reality is more subtle and context-dependent than we once imagined. Has quantum theory given us the final answer about the nature of reality? Probably not. It has provided an extraordinarily powerful mathematical tool and at the same time revealed the limits of human intuition. It reminds us to separate rigorous science from speculation and to remain open to deeper explanations. Perhaps the most important insight is this: reality does not have to align with our expectations. It can be probabilistic, non-local, contextual, and still governed by precise mathematical laws. Quantum theory does not destroy science. It deepens it. It does not promote mystical claims. It demands experimental verification and theoretical consistency. It does not deny the existence of an objective world. It refines our understanding of how that world operates at its most fundamental level. And that is what makes it so fascinating. If you enjoy thoughtful explorations of science without sensationalism or exaggeration, consider liking the video and sharing your perspective in the comments. Which interpretation of quantum mechanics do you find most compelling? Subscribe for more discussions about consciousness, physics, and the frontiers of human knowledge. Thank you for watching. And remember, the deeper we look into reality, the more extraordinary it becomes. See you in the next video.